Welcome to the third of our three-part installment on strain sensing. In this lesson, we'll explore various Wheatstone bridge circuits. We can now combine what we know about Wheatstone bridge circuits with what we know about strain gauges. So for example, I have a single strain gauge here that's measuring some strain, epsilon sub 1, and the three other resistors are normal resistors. So we refer to this as a quarter bridge circuit because a quarter of all the resistors, so 1 out of 4, a quarter of the resistors is used as a strain gauge. In the case where I have two strain gauges, strain gauge 1 measuring a strain 1 and strain gauge 2 measuring a strain 2, we refer to this as a half bridge. And then in the case where all of my resistors are replaced now by strain gauges, this is referred to as a full bridge circuit. Let's begin by taking a look at a quarter bridge circuit. For the quarter bridge circuit, we'll assume that all of my resistances are a nominal resistance R, and for the strain gauge, the resistance will be R plus a delta R, where the delta R is the change in resistance experienced by the strain gauge as it is subjected to some strain. I also have a V in, so some supply voltage for my bridge, and I'm measuring a V out between these two terminals. Now, we know from our earlier analysis that the ratio of the output voltage to the input voltage, VO over VI, that's equal to delta R, the change in resistance, divided by R, the nominal resistance, all over 4 plus 2 times quantity delta R over R. We can simplify things a bit. In the case where delta R over R is much less than 1, then I could say the ratio of the output voltage to the input voltage will be equal to delta R over R all divided by 4. Recall also that the axial strain in my strain gauge is defined as 1 over the gauge factor times delta R over R. And so I can write this as delta R over R is equal to the gauge factor times my axial strain. So if I substitute back in for delta R over R, I'll get a description of the ratio of output voltage over input voltage equal to my gauge factor times my axial strain all divided by 4. So the response of my quarter bridge circuit is inherently nonlinear due to the existence of this delta R term, this delta R over R. But this is a reasonable approximation, a delta R divided by R much less than 1, right? We're looking at small strains, small changes in resistance. But I can linearize that with a reasonable approximation. And, I end up with a reasonable approximation of my output voltage. That's equal to my gauge factor times my strain times my input voltage, all divided by 4. For the half bridge circuit, half of our resistors, 2 out of 4, are now being used as strain gauges. Once again, we'll assume all of our resistors have the same nominal resistance R. And our first strain gauge, that'll experience a resistance plus or minus a delta R1, and that'll be in response to a strain epsilon sub 1. And then our second strain gauge, that'll have a nominal resistance of R plus or minus a delta R2, and that'll be in response to a second strain, epsilon 2. So we're interested in how this output voltage is changing when these two strains are applied to my half bridge circuit. To evaluate that, let's go back to our original analysis, our original description of the output voltage, where V out was equal to the voltage divider on this side minus the voltage divider on this side, all times my input voltage VI. Now in this case, I'm interested in how is this output voltage changing with regards to these small changes in resistance, delta R1 and delta R2. We can define that then as a change in voltage, dV0, is equal to the change in the output voltage with respect to the change in the initial resistance, R1, all times dR1. And then we can continue and describe this change in the output voltage with respect to the change in each of the resistors in my circuit. Now, in this circuit, R3 and R4 are not changing, so these two terms are going to be equal to 0. And for these two terms, we're going to rely on the fact that the change in resistance with respect to that resistor is equal to the gauge factor times the strain imparted on that particular resistor, in this case, on that particular strain gauge. So the resulting description of my output voltage is going to be equal to the strain on my first strain gauge minus the strain on my second strain gauge, so epsilon sub 1 minus epsilon sub 2, times my gauge factor divided by 4, all times my input voltage. So one of the benefits here of the half bridge compared to the quarter bridge is that this description is now completely linear. So looking at the difference between these two strain gauges will define the output voltage. Let's look at a quick example of a half bridge circuit. In this case, I have a cantilever beam, and I have one of my strain gauges on top of the beam, and the other strain gauge is on the bottom of the beam, underneath. The top strain gauge, that'll experience a tensile strain, so that'll be a plus epsilon, and the bottom strain gauge experiences compressive strain, so that'll be a minus epsilon. My output voltage, V out, is equal to the gauge factor divided by 4 times epsilon sub 1 minus epsilon sub 2, all times the input voltage, Vi. And if I substitute now, this will be equal to the gauge factor over 4 times a plus epsilon minus a minus epsilon, so that'll be epsilon plus an epsilon, all times Vi. And so this will result in a gauge factor over 2 times my strain times my input voltage. So there's a very important thing to note here is that this factor of 2 presents itself in the half bridge circuit. If you recall, in the quarter bridge circuit, we had a factor of 4. And thus, I've improved the sensitivity of my bridge plus the sensor with which I was plugging that into my bridge. I've improved the sensitivity by a factor of 2 going from the quarter bridge up to the half bridge.